looking at, again, the topic of related rates. And basically, the idea in related rates is, you have objects that are moving. You have, police cars going towards a certain direction, chasing a car. You have a ladder that is falling down the side. You have a balloon that's being filled up with air. You have a cone that is being filled with sand, or they're dumping the sand out of a conical container. So things are changing. And things are changing as time goes by. So in this section, most of the derivatives will be taken with respect to the time variable. So for example, if I want to talk about how fast is the volume of this cone changing, how would I represent that as a derivative? How fast the volume of a cone changes? Well, if my volume is represented by V, I could write dV dt. This represents the rate of change of volume per unit change in time. If I'm talking about how fast is the distance changing, if I'm calling that distance x, then the distance, the rate of change of distance or velocity, I can write it as dx over dt. If I call that distance y, I can then write the rate of change of distance as dy over dt. Let's say that there was a ladder that was sliding, and this angle is theta. I want to know how fast is the angle theta changing. How would you write that as a derivative? How fast? D theta over dt. So as you can see, everything in this section is going to be differentiated with respect to the time variable, because things are changing with time. And why do they call this section related rates? Because usually they will give you one rate of change. Like they might say the ladder is sliding at a rate of 3 feet per second. And then they want another rate of change, such as the rate of change of the angle. Okay? So they give you one rate of change. They're asking you to find a related rate of change. So that's the bottom line for most of these questions. Okay, so let's go ahead and take a look at this first example. And the template shows you the steps that we need to take pretty much in every one of these questions. We always start with a graph. So in this case, we have an airplane that is going to fly over a radar tracking station, and it's flying at a constant altitude of 6 miles. Again, there are various ways that you could be doing this graph. Let's say that this is my radar station, and the airplane is coming from here, going that way. And it's a constant altitude. So this altitude here is 6 miles. And say this is my radar tracking station. Okay. The question is, if S is the distance between the plane and the tracking station, so if this distance is S, and that distance is decreasing at a rate of 400 miles per hour, what is the speed of the plane? Okay, so we have a very rough picture. This plane is going that way. This is the radar tracking station over here. It's flying at a constant altitude. And we're asked to find something. We're asked to find the speed of the plane. Okay? So, we've done the first step, which is to draw a very rough picture of the situation so we can visualize what is happening here. Second step is state the goal, because many times I think students, they don't even know what they're looking for, and they're doing circular arguments. So let's put it nice and clear at the top of our page. What is it that we're trying to find for these questions? Okay, so if we want to find the speed of the plane, let's say that I call this distance x. So speed of the plane will be the rate at which that distance is being traveled. So it's a derivative. What is that distance then? dx over dt. So the goal is to find dx over dt, the rate at which that distance x is being traveled by the plane. How fast is it being traveled? That's going to be the velocity of the plane. Okay, then they want us to write down what is given. Write down the given related rates. So for example, they said that the distance s, which is the distance between plane and the tracking station, is decreasing at a rate of 400 miles per hour. How could I write that down as a derivative? The rate of change of distance s is decreasing at 400 miles per hour. So what should I write? ds dt. Good. Somebody even thought about the negative one. It is negative because that distance is decreasing, right? So we're going to put negative 400, and the units are miles per hour. But that distance may be a variable. That rate may be a variable rate. It may not be the same rate at any given moment. We know this at the moment when at the moment when s equals to 10. Because if you think about it, when the plane is very far away, that distance is closing slowly, right? But as the plane is really, really close to the tracking station, this distance is going to be changing really, really fast, right? Right there. So it's not really a constant rate, the rate of change of ds over dt, okay? Okay, so we did the first 3 steps. We did the picture, the goal, and we wrote down the given related rates. What we need right now is, remember, since we're trying to find dx over dt, and we are given ds over dt, we need to write an equation that somehow we can get x and s out of it. We can get dx dt and ds dt out of it. What equation do you think could relate the variables in question and also maybe something that we know? For example, we know one side is 6, right? You can use that in your equation. What equation do you think we could use here? Good. You have a right triangle, right? At any given moment, you have a right triangle as this plane is moving, right? With the sides of 6, x, and s. And the Pythagorean theorem, you will see, it will get a lot of use in this chapter, in this section. So what would the Pythagorean theorem say about this right triangle? 6 squared plus x squared equals to s squared. Now, do I need a variable for the 6? I put a 6. Should I have put like a y there, do you think? Or can I keep it as a 6? I can keep that as a 6 because as time goes by, that side is not changing, right? So that is truly a constant with respect to time, right? It doesn't change as time goes by. So that's going to stay as a constant. Let me just rewrite this. So we have 36 plus x squared equals to s squared. Okay, now the next step. So see, we're trying to find dx dt, and we know ds dt. How are you going to get dx dt and ds dt out of an equation like this? Any guesses? We're going to need to differentiate both sides with respect to the time variable. And you will find that in every one of these questions in this section, once you write your equation, you will always be differentiating with respect to time. Why? Because things are changing with time. You're trying to find the rate of change with respect to time. So that's always going to be the case. Find an equation that applies in that case, and then differentiate it with respect to time on both sides. So let's do that. Derivative of 36 with respect to t would be what? 0. Derivative of x squared with respect to t would be. Now let's think about it. We're not differentiating it with respect to x, but we're differentiating it with respect to time. So x is like a function of time. It's changing as time goes by, right? So 2x times dx dt, right? The derivative of the inside with respect to the time variable, so dx dt. So as you can see, we're using like the chain rule there. We're also using like the implicit differentiation there, right? You multiply everything with the derivative of the inside, which is dx over dt, equals, how about on the right-hand side? What is the derivative of s squared with respect to the time variable? 2s. Is s also changing with time? Yeah, so s is really a function of time. It's really s of t in a sense. So 2s times ds over dt. Now, in implicit differentiation, only y got the special treatment, right? Here, basically, every variable is going to get that special treatment because every variable is a function of time, and we're differentiating everything with respect to time. Now, if you had that equation, x squared equals s squared, if you were differentiating it with respect to x, what would be the derivative of the left-hand side? 2x, right? dx would be 1, right? But you're differentiating with respect to time. That's why we're multiplying it by the derivative inside dx dt, and we keep it there. Okay. Now, what else do we know? Do we know what x is, or do we know what s is? Okay, we know what s is. They said at the moment when s equals 10. Okay, sorry, I put this in the wrong place, it seems, but it doesn't really matter. We need the equation. Is it going to let me move that? Well, assume that this is in the next step, in step number 5. For cone problems, we'll have an extra thing in that bracket space. So we differentiated already. So we've done step 5 already. Okay, now step 6 says plug in all the constants from step 3 into the equation you got here, right above here. Okay, so the constants, 2x dx dt. Do we know what x is right now? We know what S is, right? S is 10. So I'm going to put, so if S is 10, so I'm just going to put this over here, but you guys get the idea. So I have 2S ds dt. S was 10. Do I know what ds over dt is? Yeah, that was given, right? Negative 400. Okay, how about this part? 2x dx over dt. Let me leave at the moment the space for x empty. We're going to fill it in. And dx over dt is exactly what we're trying to find out, right? That was the goal. If you look at step number 2, that was the goal, dx over dt. So if I can just determine x and put it in here, I have basically solved the problem. I'll then just solve for dx over dt and we're done. Okay, how do we get x? So if you know what s is, this side was 6, this side was 10, right? So we just need to know what is this side, what is x at that moment. Some of you will already guess this. There's a famous triangle, 6, 8, 10. Right, like the 3, 4, 5 triangle is famous also. But if you don't remember it, let's just solve the Pythagorean equation here. So that side is called x. So what we have here is like 6 squared plus x squared equals to 10 squared. So x squared equals to 100 minus 36. X squared is 64. So x is 8. So since I know what x is, I can plug in this space right now. X, we just determined that to be 8. And go ahead and find out what dx over dt is by dividing both sides by 16. So on the right-hand side, I have 2 times 10, or 20 times negative 400 divided by 16. Of course, you could simplify it a little bit, etc. Or you can just put it all in the calculator and get a result. So there I'm getting 500. And what will the units be for this? Dx over dt. That should be units for x divided by units for t. So what were the units for x here? For distance, what units did we use so far? Miles, and for time we used hours. So the resulting expression will also be miles per hour. And I shouldn't forget my negative as well. The negative indicates that that distance is shrinking, or that the object is going in the opposite direction. So again, if a quantity is getting lesser and lesser as time goes by, its derivative is going to be negative.